Hello everyone, I'm Zeng Cheng. We'll study the last part of this course together. In our course, lots of mathematics will be involved. However, math is just the same as words. It's a tool to express ideas. Therefore, in our course, I'll try as much as possible to show the ideas expressed by the mathematics to you. From the previous parts of this course, we know that a linear time-invariant continuous or discrete system in zero state can be completely described by its system function model. Therefore, the characteristics of a LTI system will necessarily depend on the parameters of its system functions. For the characteristics of LTI system, we mainly focus on two aspects. One is time domain characteristics, which is the patterns of the system's dynamic response in time domain. The other is frequency time domain characteristics, including amplitude frequency response and phase frequency response. The so-called parameters of a system function refers to the coefficients of the polynomial of numerators and denominators. In other words, what kind of characteristics a LTI system will have in time or frequency domain depends on the numerator and denominator polynomial coefficients of its system function. In this section, we'll introduce the relation between system functions and time domain characteristics. Firstly, we present the system function with a zero-pole form. Then, we'll discuss the relation between the time domain response characteristics and zero-pole distribution of continuous and discrete LTI systems, respectively. For continuous or discrete LTI systems, their system functions can be expressed in the forms of zeros and poles. In this formulation, Bm is a gain factor, which will not affect the dynamic characteristics of the system. The characteristics of the system are determined merely by its zeros, zeta j, and poles, pi. For a physical system, since all of its polynomial coefficients are real numbers, its zeros and poles must be real or conjugate complex numbers. Now, let's talk about the relation between zeros, poles, and the natural response of continuous LTI systems in time domain. According to previous conclusions about time domain analysis, the natural response of continuous linear time-invariant system is composed of several different response patterns. Each response pattern has a corresponding pole. The response pattern differs from each other according to the pole and their order. However, the basic pattern is always a complex exponential form. This complex exponential function is determined by the pole pi. Hence, the system's response pattern is determined by the pole. The real part and the imaginary part of this pole will respectively affect the magnitude and frequency of natural response in time domain. To be specific, the imaginary part, omega I, will determine the frequency of time domain response. If omega I is 0, which means the pole is a real number, its natural response will be a real exponential pattern. If omega I is not 0, we'll get an oscillating response pattern. The real part of the pole will determine the developing trend of response amplitude. If the real part is greater than 0, then as t approaches to positive infinity, the amplitude of natural response rises exponentially. Conversely, if the real part of the pole is less than 0, then the response amplitude will fall exponentially. If it equals to 0, then the response amplitude will be a constant. Zeros won't change the basic pattern of time domain natural response, but they will affect the coefficients of the patterns and subsequently affect the amplitude and phase of each pattern. We can use such an intuitive graph to summarize the relation between poles and time domain natural response of LTI systems. This is a complex plane S, the real axis and the imaginary axis here. Firstly, let's look at the case where poles are real. If the pole is a positive real number, it is a response pattern rising exponentially. If the pole is a real number which equals to 0, then we'll get a constant pattern. If the pole is a negative real number, then the response pattern will fall exponentially. If the pole is second order, then its response pattern is similar to that of the first order pole. But if it is a second order pole which equals to 0, the natural response pattern will become a ramp function. Secondly, let's consider the case where the poles are complex. If the system has a pair of conjugate imaginary poles, then the corresponding response pattern will be an oscillation with constant amplitude. Its oscillation frequency depends on the value of omega I. If the poles are a pair of conjugate complex poles with positive real part, the system will have an oscillating pattern rising exponentially. If the real part is negative, then the amplitude of the oscillating pattern will fall exponentially. We can further demonstrate the relation between poles and time domain response with the following examples. This is a typical RLC second-order circuit. If the resistance, inductance, and capacitance take such values, its system function has two unequal real poles. We call such a system an overdamped system. With a step input, the output of the system will be an exponential response pattern. If we change the capacitance in the circuit from 4.7 NF to 0.22 NF, then the system will become an underdamped system with a pair of complex conjugate poles. With the same step input, the response of the system will become an oscillating pattern. For a circuit like this, are the poles of its parameters real or complex? It's a question for you. For discrete LTI systems, the relation between zeros, poles, and time domain natural response can be analyzed similarly. Likewise, the natural response of a discrete system is also composed of several response patterns. Each response pattern corresponds to a pole of system function. However, it should be noted that the relation between time domain response pattern and the poles of system function is somewhat different from that of the continuous LTI system. Due to such a difference, the pole's influence on the frequency and amplitude of the time domain response is also different from that of continuous LTI system. The module of poles determine the amplitude of response pattern, while the phase angles of the poles determine the oscillation frequency. Zeros will have the same effect as that in the continuous system. It doesn't affect the basic pattern of time domain natural response. It will change the amplitude of each pattern and the phase of oscillation pattern. For discrete LTI systems, the relation between the poles of system function and natural response can also be summarized by the following graph. This is a plane called Z. A circle on it of radius 1 is called the unit circle. We adopt the unit circle as a dividing line and discuss the poles within, on, and outside the unit circle, respectively. Let's start with the poles whose phase angle equals to 0, which means the poles are on the positive real axis. If the pole is a positive real number less than 1, then its corresponding response pattern has an amplitude falling exponentially. If the pole is a positive real number equals to 1, there will be a response pattern with a constant amplitude. If there is a positive real pole greater than 1, then the response will rise exponentially. If there is a second-order pole which equals to 1, the corresponding response pattern will be a unit ramp. Next, let's look at poles whose phase angles doesn't equal to 0. Within the unit circle, the response pattern will fall exponentially with oscillation. On the unit circle, an oscillation pattern with constant amplitude is presented. While outside the unit circle, there's an oscillation response pattern whose amplitude is rising exponentially. Other poles within, on, or outside the unit circle with non-zero phase angles will present similar amplitude response characteristics. However, from this graph, we can find that the oscillation frequency of natural response increases according to the phase angles of the poles. The maximum oscillation frequency of the time domain natural response is pi. When the phase angle is greater than pi, it's actually a repetition of the original poles. This is because the poles with phase angles greater than pi are actually the conjugate symmetric poles with a phase angle less than pi. In general, the relation between the poles of discrete LTI system and its time domain natural response has the following characteristics. Firstly, the feature of natural response amplitude is divided by the unit circle. Amplitude falls exponentially for poles within the unit circle, while it rises exponentially for poles outside the unit circle. Secondly, the oscillation frequency of response depends on the phase angle of the pole. The larger the phase angle, the higher the oscillation frequency. Thirdly, the maximum oscillation angular frequency is pi. Finally, we make a summary of this lesson. First, the time domain response characteristics of a LTI system is closely related to the system model, which is the parameters of the system function. Second, the zeros and poles of system function are also determined by the parameters of the system function. Third, the poles of system function determine the basic patterns of the system's time domain natural response. Fourth, the zeros of system function can't change the basic pattern of system time domain response, but it will affect the amplitude and phase of each pattern. Fifth, in this lesson, we have discussed the effects of zero and poles on time domain response for continuous and discrete LTI systems, respectively. In fact, the features of time domain response of continuous and discrete LTI systems can be linked by such a mapping between the z-plane and the s-plane. This mapping relation can be summarized into a table, where the origin of the s-plane, s equals to 0, corresponds with z equals to 1 in z-plane, and the imaginary axis of the s-plane is mapped to the unit circle in the z-plane. The left half of the s-plane is mapped to the area within the unit circle, while the right half, the area outside the unit circle. For the poles in the mapping areas, their time domain natural response have similar features. And that is the end of this lesson. Bye.